Hello everyone. In the part 1 of this lecture, we look at how our body could adjust to high altitude while you get a lower atmospheric pressure and subsequently a lower partial pressure of oxygen. So these are the learning outcomes for this session. We'll look at how our body will respond to a hypobaric environment, which essentially means a lower atmospheric pressure. So what will limit our survival at high altitude, and how do we physiologically acclimatize or adapt to high altitude? And last but not least, what are the health risks associated with the exposure to high altitude? And now, I would like to show you the first ever video call from Mount Everest by Sir Daniel Hughes, who was a British explorer. So I want you to observe the way he spoke and the way he breathed, even though he had an oxygen supply with him. So please watch the video.
I don't know if you know, but unfortunately they couldn't take a video camera to the summit of Everest. That's because their camera was too heavy. And here I am on an HTC smartphone using a satellite modem speaking to you live from Camp 3. It's pretty amazing really, and I can't wait to speak to you live from the top.
Just in case you were wondering, I don't have a cameraman with me. It's me and a pole, an HTC smartphone and an Inmarsat BGAN modem. And of course my red nose. It's a very proud moment to be here. It's 2.5 years in the making.
Daniel, it's fantastic. Could you do us a favour? We can hear you very clearly, by the way, and the picture is fantastic. Can you pan around?
It's also very special because, as you can see, this is the world's highest live video call. Never been done before from the rooftop of the world.
Well, we know that with increased altitude, the barometric pressure decreases. That's because the density of air has reduced. But does it change the composition of air? No, because you'll still get roughly 21% of oxygen in the air in all altitudes. And because the overall pressure has reduced, the partial pressure of oxygen, PO2, also decreases with increased altitude. And this is applicable to all other gases such as carbon dioxide and nitrogen. They also get a reduced partial pressure with increased altitude. And with increased altitude, you also get a lower temperature. So men have survived in all kinds of situations. So what we will study is to look at how our body can adjust our respiration and ventilation to different PO2 level at different altitudes. Speaking of altitude, I believe that the highest altitude we have ever been is during a flight, as the cruising altitude routinely reach about 11,000 to 12,000 meters. So that is even higher than Mount Everest. So how can we survive such a low pressure and low temperature environment? Well, you should know the answer. That's because the flight cabin is pressurized. But even it is pressurized, the air pressure inside the cabin is still equivalent to the pressure at about 1,800 to 2,400 meters above sea level. So most people will have no problem adapting to this lower pressure. But for some people who have decreased ventilation efficiency due to lung disease, they might encounter hypoxia and they might need oxygen supply. Okay, this is just to show you some extra information. If you look at the structure of an aircraft, only the passenger area is pressurized, while it's not pressurized near the luggage area and definitely not the landing gear area. So it is not a good idea hiding yourself in these areas, as you'll be exposed to extra low temperatures and pressure. And according to statistics, only 1 in 4 people who try all these things survive their trips. So at the sea level, you can see that the normal barometric pressure is at 760 millimeter, and the air you breathe in has an oxygen partial pressure of 159 millimeter. That is obtained by multiplying 760 with 21%, since you have 21% of oxygen in the atmosphere. And this value translates into a PO2 level of 100 millimeter in your arteries. So this value of 100 millimeter is basically a constant for everyone at the sea level. And upon arrival at your tissue with a resting potential of 40 millimeter, you have a 60 millimeter difference in terms of the diffusion gradient. Remember, here is your P1 minus P2 according to the Fick's law. So this differential in oxygen partial pressure drives the diffusion of oxygen from your bloodstream into the tissues. And then the deoxygenated blood will flow back to your lungs for gas exchange. So what happens if you are staying at a higher altitude, let's say at 4,300 meters? First of all, you're going to get a lower barometric pressure at 460 millimeter. And again, that is going to be multiplied with 21% to give you the PO2 level at 96 millimeter. With that, it translates into an arterial PO2 level of only 42 millimeter. So 100 at the sea level versus 42 millimeter at a higher altitude of 4,000 meters. And that significantly decreases your P1 minus P2. As a result, your body is now struggling to provide oxygen to a tissue, especially to the peripheral tissues. So something needs to be changed. What are they? Well, the answer is ventilation is needed to be changed. So our body responds to a hyperbaric or a low pressure environment by increasing ventilation. Again, as altitude increases, the oxygen partial pressure decreases at the same time, and our tissues might not be getting enough oxygen supply. So that will be detected by chemoreceptors, and they will send a signal to our brain by increasing both the rate and the depth of ventilation. So this is what you have heard and observed from the video just now. So by increasing both the frequency and the volume of our breathing, we manage to compensate for the drop in PO2. So from this second diagram, you can see how with a lower PO2, our minute ventilation is boosted. But in order for the oxygen to be circulated efficiently, we also need the cooperation from the circulatory system. As a consequence, we get an immediate boost to our heart rate and cardiac output so that this oxygenated blood can be delivered to the peripheral tissues. So what do we call the scenario when we breathe in faster with larger volume? It is called hyperventilation, and it's the countermeasure towards hypoxia or the lack of oxygen supply to our tissues. So when hypoxia happens, the low PO2 level activates our peripheral chemoreceptors. That increases our ventilation and subsequently the PO2 level within our arteries. But there is a problem. When we undergo hyperventilation, not only we breathe in faster, but we exhale faster as well. In other words, that decreases our carbon dioxide partial pressure. And with that, it removes our carbonic acid and we observe a rise in pH due to alkalosis. Not only this low PCO2 level will be detected by the central chemoreceptors, which will send a signal to reduce the rate of ventilation. As a result, PCO2 will rise again and you will take a slower deep breath. But still, the oxygen demand will not be met. So this breathing cycle or pattern is known as the Cheney-Stokes breathing pattern, and is characterized by a set of rapid breathers, and then with one pause in breathing, then one deep breath under the control of your central chemoreceptors, and back to hyperventilation again. So this is what can happen to you if you are at a high altitude. And when this happens, you will need an oxygen supply, as you will never meet your oxygen demand through this breathing pattern. So it sounds something like this. Let me demonstrate for you. I hope you get the idea. Well, I'm passing out. So again, at a high altitude, we undergo hyperventilation. and that leads to the renormalization of the PO2 level, but at the expense of increased carbon dioxide exhalation. As a result, we will get the respiratory alkalosis. So to compensate for this change in your blood pH, your kidneys are going to respond by excreting out more bicarbonate ions from the body. That's because by doing so, we are pushing this equation towards right-hand side, favoring the production of more protons. In other words, what you're trying to do is to generate a metabolic acidosis to counter this respiratory alkalosis during hypoxia. And that could be achieved by three different ways. Number one, a reduction in bicarbonate absorption in your proximal tubule. So reduced absorption means increased excretion of bicarbonate ions through urination. Number two, you also get a reduced proton secretion by the alpha intercalated cells into urine. So you retain more protons to counter the alkalosis. Number three, an increased bicarbonate secretion by the beta intercalated cells into urine. So that accelerates the removal of the bicarbonate ions. So essentially, both alpha and the beta intercalated cells, they are essential in what we call the acid-base homeostasis, and they do so by adjusting the amount of protons and bicarbonate ions in the system. And sometimes acetazolamide is prescribed as a drug to the mountaineers because it is an inhibitor for the enzyme carbonic anhydrase, which is responsible for the generation of carbon dioxide and alkalosis. So aside from increased ventilation or hyperventilation, a second adaptation towards a high altitude is increased 2,3-DPG production by your red blood cells. So you have learned this during my previous lecture on blood. So with more 2,3-DPG, the oxygen binding curve is shifted towards right-hand side, favoring the release of oxygen during hypoxia. But when you have a higher oxygen dissociation rate, it also means a lower oxygen affinity or a lower oxygen binding rate. So that problem is compensated by an increase in the ventilation rate. And the whole purpose of having 2,3-DPG is to ensure or to improve oxygen delivery to peripheral tissues that might otherwise become hypoxic at a high altitude. So both hyperventilation and 2,3-DPG production are short-term adaptations to altitude. But what will happen if you stay longer at a high altitude? So you are staying at a high altitude for weeks or months, you're going to get some long-term adaptations. And one of which is increased hematocrit. So if you can remember, hematocrit refers to the percentage of red blood cells in your blood sample. So initially, you will get a boost in hematocrit by a reduction of plasma volume. So this is achieved easily by increased urination or by the loss of water through increased ventilation. That's because when we breathe out a lot of water vapor. So with hyperventilation, we lost a lot of water at the same time. As a result, your hematocrit level will rise above 42%. But if you stay for more than 2 weeks, your body will react by producing more red blood cells. And this process is known as hemapoiesis. It requires the hormone erythropoietin released by our kidneys. And as a result, you'll get more red blood cells production and a higher oxygen transfer capacity at a lower PO2 level. And this mitigates the effect of hypoxia. Not only this, another long-term adaptation to altitude is increased production of capillaries. So the process of growing more blood vessels is known as angiogenesis. So with more capillaries, this improves the diffusion of oxygen in between cell and the capillaries by shortening the distance in between them. So you also get a larger surface area for gas exchange in your lungs. And in addition, your body will produce even more mitochondria and respiratory enzymes such as cytochrome oxidase to improve metabolism under a lower PO2 level. And now let's take a look at the acute mountain sickness which might happen when we fail to respond and adapt to the high altitude. So the severity of this sickness is depending on the rate of ascent, so we should always slow down and allow physiological adaptations to happen. And it will be more prominent at a high altitude, which is higher than 2,500 meters. And it also depends on the length of time at that altitude. And if we exert ourselves too much physically, that will make the situation worse. And it has everything to do with our fitness level and our physiological susceptibility. So, what are the major symptoms of the acute mountain sickness? Well, we'll feel headache, fatigue, dizzy, or could even get cyanosis if peripheral hypoxia is out of control. So cyanosis is characterized by this bluish discoloration on our extremities, which are the color of the deoxygenated hemoglobin. And how can we recover from these symptoms? Well, just get down from the mountain or get ourselves some oxygen supply. And sometimes the acute mountain sickness can get even worse or more serious if we get some fluid accumulation in our lungs, which is known as the high altitude pulmonary edema, or fluid accumulation in our brain, which is known as the high altitude cerebral edema. Well, we are not going to elaborate much on the edema with acute mountain sickness, but here is what happens in HAPE, or the high altitude pulmonary edema. So when you experience alveolar hypoxia, there is a lack of oxygen in your lungs. This triggers hypoxic pulmonary vasoconstriction, a complicated process that improves gas exchange. But with the constriction of your blood vessels, it causes an increase in the capillary pressure, and that could lead to damage and leakage of your capillary wall. As a result, fluid will start to build up in your lungs, and that could further impair gas exchange and oxygen delivery.